All right, so today we're going to talk about convection. And convection, the easiest way to put it, it's all it's all a transfer of heat. But when we talk about convection, we're usually talk about circulating the air. And then the transfer occurs because the air molecules are more likely to run into each other. So air molecules are kind of spread out, and if we have a fan, that fan will blow the air, and then the warm molecules will bump into the cold molecules, and then the heat will transfer. So very similar to what we discussed before. And so I'm going to add another thing here. So I've got this big old pot thing here. And let me slide this down. So normally when a pot of water boils, what happens is inside the pot of water, there's this thing where the actual water circulates, okay? And man, I am having a difficult time with this. Okay, there it goes. Close enough. And so what does that mean? Well, the heat transfer, convection plays an important role in heat transfer inside of a pot of water. The heat transfer from the other parts of the pot is mostly convection. Hotter water expands, increases the density, rises. Then as it so like, just let me give you an example of this. I have one little lonesome water molecule here, right? It absorbs heat energy from the bottom. As it gets hotter, it expands. The density changes, it's less dense, and so then it comes up here. As the molecule continues to heat up, at some point, usually right up here, it transfers its heat energy to the surrounding water molecules. And so then it loses some of its heat energy and it comes down and eventually comes back up, and then it's warmer down here too. So what's going on essentially is that you have this heat transfer, but it's circulated, right? So because of the circulation, your heat gets transferred up towards the top, right? But then also the cooler molecules will naturally kind of come down, and that's what causes this circulation motion, okay? So let's do a little math with that and see how that actually works in the real world. So I'm going to put, let's copy this real quick. So furnaces in general will want us, that what they do is the way that our furnaces in our house work, most of them, not all of them, but most of them, they have a fan, and that fan's only job is to circulate the air. So let's read this real quick. It says most houses are not airtight. Air goes in and out the doors and windows through cracks and crevices, following wiring and switches and outlets. So there's lots of places for the air to come in contact with other air. And so the heat wants to travel to something that has less heat, and it gives off its heat. And so it says the air in a typical house is completely replaced in less than 1 hour through this process. Suppose that a moderately sized house inside has the dimensions of 12 meters by 18 meters by 3 meters. And that all the air is replaced in 30 minutes. Calculate the heat transfer per unit in watts needed to warm the incoming cold air. In other words, cold air is seeping in. You're losing hot air. What do we got to do to calculate the heat transfer per unit in watts needed to warm the incoming cold air by 10 degrees Celsius? Okay. Thus replacing the heat transfer by convection alone. So this is not too difficult. What we need to remember is that heat energy can equal the mass times the specific heat times the change in temperature, right? And then also, because they're asking us to give them a thing in watts, that means we're going to need joules per second, or in this particular case, heat per time, right? 1 joule per second is watts. And then also, because the heat transfer is 10, I know that delta T, capital T, is equal to 10 degrees. And so what else do we need? Specific heat. We have the time. So I'll have to do some conversions on the time. The time is 30 minutes. And so we have to, I think that's 1800 seconds if I think about that for a second. And then lastly, air is mostly like nitrogen and oxygen, and so the specific heat is 1,000 joules per kilogram, and you can look this up, or not, yeah, kilogram degrees Celsius, and this is degrees Celsius. And so, shoot, let me think if there's anything else. Specific heat here. And that's the weighted average between nitrogen and oxygen. So that's nitrogen and oxygen. And remember, these are both diatomic, so usually nitrogen's a diatomic molecule, as is oxygen. And so we're just kind of averaging it somewhere, and this is just an estimate. And then also we have to consider the density, right? Because to get the mass from the air, okay, so mass is a tricky one, right? So mass for air is going to be a little tricky, because how do you find that? Well, we have a volume, okay. Well, how do I find that? Well, remember that there's this relationship between the density of air and the velocity. So this is going way back, right? So then what's the density of air? Well, 1.29 kilograms per meters cubed. And then the volume is going to be this 12 times 18 times 3 number for meters, right? That comes from here. This is the volume, the approximate volume. And so the mass of that air, believe it or not, is 836 kilograms, if you plug all that together. So a house this size, 12 meters by 18 meters by 3 meters, the air weighs 836 kilograms. All right, so I have the mass, I have the specific heat, I have delta T, I can find out the heat, which is Q, and then the time is just 30, the time is just 1/2 of 3,600 seconds, right? So remember that 1 hour equals, I hate when that does that. No. Oh, shoot. I lost my thing, but that's okay. We'll just rewrite it down. We did the calculation. The only bad thing about the software. Okay, so then my mass of the air was 836 kilograms. And then remember that 1 hour equals 3,600 seconds. So then T is 30 minutes, or 1/2 of that, which is 1,800 seconds. So we're going to plug all this stuff in. So first let's find Q. So Q is equal to the mass, which was 800, and I'm going to I want you guys to write down your units, but I don't have enough space, so I'm going to skip that. Times the specific heat, which is 1,000, times delta T, which is 10. So it's a big number. Okay, big number. So the heat is 8.36 times 10 to the 6th joules. And then, so if I want to know the watts, remember that watts is equal to joules per second, or in this case, Q over the time, t, lowercase t, or 8.36 times 10 to the positive 6 joules per 1800 seconds. Okay. So then if you do the math on that, it's actually, oh, you're kidding me, right? Okay. Let me do this a different way. This thing is acting weird today. So then Q T, because I'm running out of room, QT is equal to 4.64 kilowatts. Now that's per half hour, so it's a little more than 9 kilowatts an hour to do that. So there's that. So what does all this mean? That the rate of heat transfer is equal to the power consumed by about 46 100 light watt bulbs. Newly constructed homes are designed for a turnover time of more like 2 hours. So that'll cut that down significantly. And that's why it's important to have insulation and do all the things you do to kind of trap the heat in the home. So it, not only that, but doesn't allow the cold air to come in. Because when the cold air seeps in, then the heat gets transferred to the cold air. So that's why we have furnaces. All right, we've got cold air coming in. If the cold air didn't get in, then the energy would just kind of, you'd reach a state of equilibrium, but the air outside is much colder, so it escapes. So anyways, that's that one particular problem. There is a chart in the book that talks about moving air and wind speed and based on temperature. So you'll need, and I'm just going to throw it, it's in the textbook, but you'll need some of this information that you'll need for your homework, right? And it just says moving air temperature, so at 5 degrees, your wind speed needs to be 3 meters per second. And so, yeah, so that's what, where, and basically it's a chart where you have a moving air temperature and then the wind speed, all right? And basically cold wind is much more chilling than still cold air because convection combines the conduction in the body to increase the rate at which the energy is transferred, right? So when you feel a cool breeze in the wintertime, what you're really feeling is the heat leaving your body quickly because the cold air molecules are hitting your body because there's a little bit of a draft. And that's why temperatures are weird. Like in the wintertime, you want the furnace like 72 degrees because you feel cold. Well, yeah, the heat is literally leaving your body because the draft is constantly, air molecules are constantly pulling the heat away from your body. But in the summertime, 72 almost seems too hot, right? Why? Because the transfer is kind of reversed. If your house, if it's really hot outside and the heat seeps in, it's different because then the warm stuff hits your body because the draft now is carrying heat energy, and then your body is absorbing the heat. So that's kind of what goes on there. So anyways, this is a chart that you'll use that compares the air temperature to the wind speed. And we'll use an example so you know what's going on. One of the nice things about fur, and this was in the textbook that I thought was kind of a neat thing, fur actually is a good insulator. So a lot of animals have fur, and the way that's a good insulator is that, whoops, there it is. The circulation is contained to the fur. So it has many convection loops that goes on in the fur, and so that keeps the body warm, keeps cold air out. It's an insulator, it keeps it separate. We mimic fur with actual insulation that we install in our homes, in between the walls. So this would be like the inside of your house in the drywall. This would be insulation, and then this would be the exterior of the home. And the more layers that we could put, the better off we'll be. So let's use an example, pulling numbers from the chart and all that stuff. So one more example for convection. And really notice there wasn't like a new formula per se. We're just, the applications are different using the formulas that we've had in the past. So the average person produces heat at a rate of about 120 watts when at rest. At what rate must water evaporate from the body to get rid of this energy? Remember, evaporation might occur when a person is sitting in the shade and surrounding temperatures that are the same as the skin temperature, eliminating heat transfer. And so evaporation is kind of like, they're really saying sweat, right? So when we sweat, the heat energy kind of goes with the sweat, and then the sweat on the outside of our body transfers the heat to the surrounding air molecules. And so it's a way for our body to regulate temperature. And so how do we figure this out? Well, we know we're talking about, they give us wattage. So we're going to have to, from there, remember that a watt is just energy, joules per second. And when we talk about heat transfer, it's going to be heat energy over time, right? And the time is something that we could do, but we know that this thing has to equal 120 watts. Okay? All right, so now that we know that that equals 120 watts, we know that that also equals 120 joules per 1 second. Okay. And then also Q can equal, because we're talking about evaporation, the mass times the latent heat for vaporization. All right, so then QT could actually equal mass times the latent heat for evaporation over time, which also equals 120 watts. And then this is an interesting thing. I can find the mass over time. If I do algebra, if I divide both sides, oops, I made one little minor mistake here. This should be joules per second and not watts. All right, so that we're going to leave this as joules per second. Right, so then I have 120 joules per second divided by the latent heat for vaporization, right? Okay, we're getting there. So then, notice I don't know the mass and I don't know the time, but what I can find out is the latent heat, right? And so the latent heat, there's one of your I'm trying to find a good one. So sweat is like mostly like water, but it also has like some salt in it. So I got to go back to the tables and determine what latent heat I should use. So I'm just reading to make sure. So I'm going to click on the table. You guys can't see what I'm doing on the screen, but I'm going to click on the table that has all of the latent heat coefficients for vaporization. And this is a tough one because it gives me water, but the textbook doesn't use water. I would use water. Let me see what salt is if they have salt on here. Yeah. You can Google this, and then this is part of the challenge for Googling this. So the latent heat they have is really kind of for sweat. And when I Googled it, and if you round it up, so this is kind of gross, but the latent heat for sweat is about 2430. So when I Googled this, it was 2426. And basically you have mostly water, and then you also have some salt or sodium, and because water is like 233-ish, or not 200, 2330-ish, and then sodium is well, let me go back to the table. Maybe they just added sodium. Water is 2256. Water is 2256. I don't see sodium. Yeah, I bet you they just added water and sodium or something, because water is like 2256. Okay, so anyways, that's what we're going for. So then this becomes 120 joules per second all over 2430. And that's going to be joules per gram. And so these cancel. And so then what I get is that m over t, the mass divided by time, is equal to approximately 0.0494 grams per second. Okay, and that's basically it. And they convert it to grams per minute, but that's okay. I think that's pretty much it. There's some, yeah, that's it for the notes. So when you go to do the homework, I think you guys will have some questions on your homework, but I just want you to work on the homework, and that's it. I'll post the problem set in Canvas.